Good morning, everyone. Thanks for taking the time this morning to sit in on this presentation. The title of the presentation is Managing Flow Through Domestic Hot Water Systems While Performing Thermal Disinfection. My name is Tom Ruggierio. I'm Business Development Manager at Thermomegatech. My partner in crime is Aaron Markward, who's a Sales and Product Manager at Thermomegatech. Now, before I get started with the presentation, I just wanted to give you a little bit of background as far as why we created this presentation. Prior to COVID pandemic, Aaron and I traveled the country, meeting with engineers and contractors, discussing balancing domestic hot water systems. When speaking with engineers tasked with designing disinfection systems, whether they be thermal or chemical, we sensed a fair amount of frustration on their behalf due to the lack of a standard guidelines for them to follow to design effective disinfection systems, whether it be thermal or chemical. They felt they were kind of left on their own devices. So I developed this presentation to create an awareness with the plumbing engineering community and build some momentum towards creating standards and guidelines to institute best practices when designing disinfection systems for Legionella mitigation. So the agenda for today's presentation will start off with a brief overview of thermal disinfection, discuss some of the implementation challenges, define the elements of a control system that we'll be using for this system, approaches to automating the process, cost versus safety, and then end with a summary and next steps, and then a Q&A period. So the background, thermal disinfection is one of the primary methods used to mitigate Legionella in a domestic hot water system. Chemical disinfection is the other primary method. Management of this process can be expensive and time-consuming. As I recently stated, the plumbing engineering community is looking for direction on how to implement such systems, and the healthcare industry is looking towards us, the plumbing engineering community, for some direction and help. At this point, there is no standard approach to managing this process. So some of our objectives are first to introduce two concepts as potential methods to address this problem, then provide the plumbing engineering community with concepts that can be built on to effectively manage the thermal disinfection process. What I want to add here is the two concepts that you'll see today are not in any way, shape, or form, totally vetted or implemented, but it's a starting off point for the whole plumbing engineering community to look at and to build upon, and at the end of the day, to basically develop some best practices. The ultimate goal is to include these approaches in standards that are currently being developed by ASHRAE, ASPE, the VA, OSHA, and so on. So this presentation is not about the pros and cons of thermal disinfection for Legionella mitigation, and it's not about debating the effectiveness of thermal disinfection over other methods presently being employed. One size does not fit all. One of the things I've learned over the last couple of years regarding Legionella mitigation is that typically more than one solution is required to have an effective Legionella mitigation system. So it's not just thermal disinfection or chemical flush or filtering. You need to basically combine different approaches to really optimize your Legionella mitigation. This presentation is about formulating approaches to manage the thermal disinfection process in a controlled and automated manner. Notice I said automated, not manual. The aim is to create awareness, introduce approaches that minimize cost, time, and resources, and maximize staff and patient safety. We also want to start a formalization process. So thermal disinfection overview. In a broadly defined explanation here, the use of moist heat to kill bacteria and viruses by exposure to a specific temperature for a set amount of time. A thermal disinfection is currently one of the primary methods used to mitigate Legionella growth, but definitely lacking consensus on how to manage that process. So in the simplest terms, the thermal disinfection process is basically sending very high temperature water over 160 degrees Fahrenheit, flushing it through all the components of a system for a minimum of 20 to 30 minutes. When I say flushing through all the components of a system, I'm including the actual fixtures. Now, I have seen some things by CDC where they talk about just a 5-minute flush, and but the preponderance of information that I've read recently discusses 20 to 30 minutes as the amount of time to flush through the system. So the pros of this is that this thermal shock of the isolated components can be very effective in mitigating Legionella. That's stated in ASHRAE 12-2020. The cons of this is that the management is expensive and time consuming. Now, I don't want to mislead anybody thinking that thermal disinfection is the only mitigation process that's expensive and time consuming. They all are expensive and time consuming. So please keep that in mind, whether it's thermal disinfection, chemical flush, or whatever. It does require a lot of expense and time to fully implement this. So some of the implementation challenges. The management difficulties of thermal disinfection, it is, again, a time-consuming process. The faster we try to flush the system, the more management resources it's going to consume. You can imagine trying to thermal disinfect a whole domestic hot water system that may have 50 to 100 risers in it. There's going to be a lot of resources that need to be available to make sure that the patients and the staff are safe, because you're going to be flushing 160-degree water down through the fixtures. Because of that difficulty of doing this and the cost of doing this, there tends to be more of a reactive versus a proactive approach to implementing a thermal disinfection process. So what that means is, instead of on a periodic basis, the hospital determines that they want to do a thermal disinfection, they kind of tend to stay away from it, and they wait till an event happens, unfortunately, that somebody basically contracts Legionella, and then what they'll do is go ahead and do some emergency thermal disinfection of those areas that they determine were infected by it. So it's highly impractical to assume that you can flush an entire domestic hot water system at one time. And that's one of the things I got out of talking to a lot of the engineers that were tasked with this process, is that I think their basic assumption was that they were going to basically flush the whole system at one time. Well, if you look at the sketch on the right here, I'm only showing 4 branches of a domestic hot water system. It could be as many as 50 to 100 in some locations. And then you can imagine if you were sending 170-degree water through all those branches and all those fixtures at one time, that the hot water capacity that you would need would be tremendous to have to do that all at one time and to do it for 20 to 30 minutes. Also, the resources required to manage all those fixtures that are being flushed at 160 plus water would also be a very difficult task. And again, you're compromising staff and patient safety, and so therefore there is that reluctance to proactively flush. Flushing that whole system at one time is not recommended by ASHRAE 12-2020. And the other issue is when there is a Legionella event, and let's say in this little sketch here, it was branch number 3, where they determined there was excessive Legionella bacteria that caused a problem. This kind of a system, if it's set up this way, you wouldn't be able to flush just that branch. You'd have to flush the whole system at one time. So again, there is that reluctance. So what are the elements of a control system? So again, I'm going to present 2 approaches to more automating the thermal disinfection process. And I want to discuss first the type of componentry that we'll use in implementing that. So there are 2 sets of basic elements for these approaches that I'll be outlining. The first one is use of solenoid valves, and the second is controls. Regarding solenoid valves, there are two types that we'll be talking about today. The first is a two-position, two-way solenoid valve. Two-position means two states, that the valve is in two states, and two-way means that there are two ports to the valve, in this case an input port and an output port. The next type of solenoid valve that we'll be using is a two-position, three-way solenoid valve. Again, two positions meaning two states, three-way meaning three ports. Our three-ported valves, our three-way valves, will basically have two inputs and one output. There are also three-way valves that have one input and two outputs used for diverting applications, for instance. From a control standpoint, the first thing we'll talk about are enunciator panels, then HMI PLCs. HMI stands for Human Machine Interface. PLC stands for Programmable Logic Controller. We'll discuss wireless controls and building management systems. So the very first element is a solenoid valve. It's what we call a two-position, two-way valve. It's electrically controlled, not pneumatically or hydraulically. The NO stands for normally open, meaning when there's no power to the valve is in an open position. So if you look at the diagram on the left, you'll see at the top electrical control signal, 0 volts means there's no power to that valve. In that normally open state, the water on input 1 is allowed to flow through that valve through the output. On the next diagram to the right, you can see I have 24 volts applied as the electrical control signal, which is the typical voltage used for industrial control systems. You can also get solenoid valves that are powered by 115 volts AC, 24 volts AC, 5 volts DC, etc. But typically 24 volts DC is the power source in most industrial control applications. So when that 24 volts is applied to a normally open valve, whatever's sitting on input 1 is not permitted to flow to the output, so that input is blocked. So to kind of rehash this and summarize it again, two-position, two-way means two states, two ports. Normally open, meaning no power to the valve. The flow is free to go from input 1 to the output. The next device we're going to talk about is another solenoid valve, and this is a two-position, three-way electrical control valve. So if you look at the left-hand diagram, basically you have no volts applied in this case, and the input 1, the flow on input 1 is allowed to go through the valve to the output, and input 2 is blocked. When we apply 24 volts to this valve, the input 1 flow is blocked, and the flow from input 2 is allowed to go to the output. So once again, just like the two-position, two-way valve, this being a two-position, three-way valve, it has two states. The state with no power being applied, and then the state with 24 volts being applied. So these are the two types of valving we'll be using in the upcoming approaches that I'll discuss. There are all types of other solenoid valves as well, but this is what basically we'll be focusing on. So from a control standpoint, there's 4 different examples of controls that we'll talk about. And basically the controls, that's kind of the brain that's basically putting power to the valves or taking power away from the valves. So the first controls example is what we call an enunciator panel. This is the least expensive, least flexible of all types of controls. And by being least flexible, it's also prone to error because of this requires heavy interface with the operator. So I first apologize for the quality of this photo, but it's good enough for what we're going to discuss here real briefly. If you look at the upper left-hand corner of the photo, you'll see alarm 1. So basically that would be an example of a switch that's basically wired directly to one of the solenoid valves. And these switches are typically all backlit, meaning once you press on that switch, if it's energized, that alarm 1 light, that white background will become very bright white, meaning that there is now power through that switch. And same thing happens for all the other switches in the enunciator panel. So what you can see here is, although it's a very inexpensive device, if you're trying to do something like a thermal flush or thermal disinfection, you're going to be heavily dependent on the operator of these push buttons to make sure they're pushing the right buttons to effectively do the thermal disinfection. So very inexpensive. Every switch is wired to a solenoid valve, but very inflexible and prone to operator error. The next device is what we call HMI PLC. HMI stands for Human Machine Interface and PLC for Programmable Logic Controller. So this is basically like two devices in one. So the photo of the example here is, this is a touchscreen, color touchscreen HMI PLC. And it has a lot of flexibility to it because it can be programmed to turn on and off valves based on any kind of a sequence that's programmed into it. The front display is a color touchscreen display, so that's the window to the operator. And basically that can be programmed to institute all types of recipes for doing the thermal disinfection of the system. So that's kind of the front end of the system, the operator interface part of it. The back end is the PLC, the Programmable Logic Controller. That's kind of the interface, the PLC, from the switches back through the operator interface, the HMI. And these devices have come down a lot over the years in pricing. This this device shown here is a 5x7 color touchscreen with a number of outputs, say on the order of between 50 and 100 outputs it can control. And the cost of that device for the hardware is basically around $700. So there's a lot of power there for a very low cost. Where the cost comes in with this type of device is actually the programming of it, because you have to program the operator interface as well as program the PLC. Now the tools to do this have evolved a lot in the last 10 years, and they're at a point now where really with some basic instruction, a high school student or a college student could definitely program this device, especially for our application, which is relatively simple and not very demanding on the controller. The next device is a wireless enunciator panel. It's kind of like a hybrid of the first two we talked about. It has that look of an enunciator panel on it, but it's also programmable, so you can program different sequences and things like that with it. The big advantage of this device over the other ones is that it is wireless. So the operator doesn't have to be stuck in a control room or a mechanical room to initiate the thermal disinfection process. They can actually walk around the building, different parts of the building, and visually observe what's going on as well to make sure everything is going right when they're doing the thermal disinfection. And lastly is the BMS, a building management system. These systems have been around for well over 30 years. They're used frequently in big buildings and also to control HVAC. We're starting to see more and more of these kind of working their way into plumbing systems. So one of the things to keep in mind as we go through these examples, and you're charged with the challenge of basically doing some type of an automation process for thermal disinfection, I would recommend first you talk to the controls people on the project to see if there is a building management system in place or that will be in place, because what you may want to do is piggyback off of this building management system to do your thermal disinfection. So approaches to automation. Here's now we're going to go through a couple of examples on how to automate the thermal disinfection process. So the first scenario we're going to talk about is with a single hot water source. The second example you'll see is with two hot water sources, just to give you a little preview of what's coming up. Like this one is just with a single hot water source in a domestic hot water system. So what you see here in this sketch is basically the normal overview of a domestic hot water system. Starting from right to left, you have your return line with the down arrow. Then you have your basically balance valves that have thermal disinfection capability. The supply lines to the left of that with fixtures. The thing that's different from typical domestic hot water systems is we've introduced these two-way control valves that we already talked about. So in this example here, these two-way control valves are all basically in the on state. And as you look at the bottom here, I have a single hot water source combined with a mixing valve that has capability of providing either 140 or 170 degree water. So the state of that hot water system right now is producing 140 degree water through the mixing valve. through all the branches in the system. The two-way control valves are all in the on position, so this is kind of business as usual. Everybody's getting their hot water. Everything's flowing back through the return line. So now what happens is there is a decision being made that they want to do a thermal disinfection of the domestic hot water system. So the first thing you do is, in this type of a system, you basically turn off all of the two-way control valves. This diagram only shows the top one being on, but you would initially turn off all the two-way control valves. You would change your mixing valve output hot water temperature to 170. You would make sure all the fixtures are on at the farthest branch, because that is going to be the first branch that you're going to do the thermal disinfection for. So now you have a scenario where all the valves are off, nothing's flowing through the system, the water got changed to 170°F, and all the fixtures are open, and whatever personnel are there to manage the process are there observing the fixtures to make sure there's nobody around there that would get hurt or scalded by the hot water. So then the next sequence from your controller is you turn on that two-way control valve at the top, the furthest fixture. That will basically then cause the 170° water to now start flowing through the supply line, back through that farthest branch, and back through the return. So this will be done for a period of 20 to 30 minutes. Also, your controllers, you can actually put timers in your controls that will actually run this for 20 to 30 minutes and then shut it off. But basically, we'll flush that first branch for a period of 20 to 30 minutes. And that branch will then be thermally disinfected. Next, you go to the next farthest branch. So now the top branch, before that was just thermally disinfected. Now that two-way valve is turned off. The second one is turned on, and all the fixtures are turned on. And now you're flushing that second branch with 170° water for 20 to 30 minutes. And you do this sequentially from branch to branch to branch till you get to the one closest to the hot water source. And then when that's all done, your system is totally thermally disinfected, all controlled automatically without the worries of operator interference or operator error. So one of the things, or a couple of things to discuss about this while we're looking at it, is number one is while you're thermally disinfecting a given branch, all the other branches in the system are off. So there is no hot water flowing to any of those branches. So basically that whole domestic hot water system is without hot water when you're doing thermal disinfection. The other thing to look at with this is versus trying to flush the whole domestic hot water system at one time. If now with this type of a system, if you have a Legionella event and it was determined that branch 3 had excessive bacteria and caused people to get ill because of it, what you could do with this type of system is basically go in right away, turn on that two-way valve to the on position, turn off all the other valves, turn your hot water source to 170, turn your fixtures on, and basically flush that one branch that's in question. So with practice, you could see that you could basically, as soon as there's an instance of an issue, you could basically go in and within an hour have that branch thermally disinfected, which is a huge advantage over the traditional way people are trying to implement this. So it's very powerful. So in summary of that the single water source, it is relatively inexpensive. You basically have a hot water source that has 2 output temperatures. This is better suited for retrofits than the next example we'll go over because it doesn't require an additional hot water heater or supply line. Because it's automated, it minimizes the resources required and also shortens the overall disinfection time. The other thing, though, to keep in mind is that the domestic hot water source will be out of service while you're doing this process. Next, we're going to talk about a dual hot water source system, which will provide a lot more capability, but the trade-off will be additional expense. So this diagram here is shown under normal operation, a similar sketch to what I just showed going from right to left. The differences are, instead of a two-way control valve, we now have showed the three-way control valves that we introduced earlier in the presentation. In addition to the three-way control valve, we also have 2 hot water sources, a at the bottom left there, 170 degree and 140 degree, and an additional supply line, which is shown in gray. So under normal operation, the input one of all those three-way control valves are on, permitting the 140 degree water to flow through all the branches, just like it would do normally. So nothing different there. Now a decision is made that they want to do a thermal disinfection of the domestic hot water system. So you go to this next drawing here, and what happens in this case is that your 170 degree water is now on, and the farthest branch number one at the top, the fixtures are on, and instead of the water flowing from input 1 to the output, it's flowing from input 2 to the output. So what you can see now is that that top branch is being thermally disinfected of 170 degree water. The key and major difference of this approach versus the single hot water source approach is you see all the other branches below that, they're still in service. They're still receiving the 140 water. So the only patients or staff members that are out of service are the ones in that top branch right now that are being flushed for that 20 to 30 minutes. So a huge advantage if you can afford the ability to have a second supply line and a second hot water heater. This offers a huge advantage over the first approach because you're basically keeping most of the system operating while you're doing the thermal disinfection. So once you do the first branch, then you move to the second branch. So now that top valve is basically turned, input 1 is turned on to originally, and now the 140 is flowing through that branch. And now you're disinfecting the second branch. And you turn input 2 of the second branch on, and that hot water is flowing through that branch. So that branch is now being thermally disinfected for 20 to 30 minutes. And you go on down the line from branch to branch to branch. Now, the other thing, again, like with the first system, is if there has been a Legionella event detected, and it was, say in this case, it was branch 4 that was determined to have very high bacteria count, again, with your control, you can automatically go to branch number 4 and thermally disinfect branch number 4 while keeping everything else in service. And you could do that again with practice, with the right rehearsals. You could do that again within an hour. So very powerful. Now, the one thing I'll show you in the next diagram, which I didn't discuss previously, just to get the concept across to everybody, is the fact that in the example I showed previously with the dual hot water source, the primary hot water supply line was not being flushed, okay? So everything was being flushed. All the hot water was going through the 170 degree hot water supply line. So if the determination is made, and I can't see why not, other than the additional cost, that you also want to flush the primary hot water supply line, what I showed here in the gray is 2 additional valves being introduced. A two-way normally closed valve. Normally closed meaning when there is no power to that valve, there is no flow. And then to the right below that is a 3-way control valve, just like we talked about previously. So in this case, if you want to thermally disinfect your primary supply line, you would basically energize that 3-way control valve so that input 1 is on, and you would make sure that the 2-way control valve, that there is no 170 water flowing through that. So now when you do your first branch, your furthest branch in the system, you basically put it in this type of scenario, and it will basically show, it will disinfect the furthest branch first, and at the same time disinfect the primary hot water supply line. So I wanted to introduce that secondly in this example, only because I didn't want to confuse it until we went through the first part of it. So again, this is a way, once you get comfortable with these valves and the controls, you'll see a lot more ways of doing these types of solutions than I'm showing here. This is just to kind of get this whole approach kick-started, basically. So one of the things we haven't talked about in those 2 examples is the other part of the domestic hot water system, the pump and the return. So when you think about in a 2 hot water system, basically what you're doing now when you're flushing the system or disinfecting one of the branches, you have 170 degree water going through one of the branches and 140 degree temperature going through all the other branches. So in that case, if you think about it, depending on the number of 140 branches not being flushed versus the 170 that are being flushed, the return temperature is going to be higher than the 140. So that makes things a little tricky, but the thing we have going for us is that now, because you're flushing, it's an open system, so you can add water to it, unlike a closed system. So if you think about the water temperature now coming back through the return could be higher than 140, and it depends on the ratio of, again, branches that are being thermally disinfected against ones that aren't. Let's say you had 10 branches in a system, one was thermally disinfected, the other 9 weren't. That would kind of mean, in theory, that your 140 may be 10% higher than normal, that type of a scenario. So if you have a 50 branch system, it would only be 2% higher than normal. So basically, you have this water going to one pump, and what you have to do then is divert the flow between the 2 hot water heaters, and you divert that flow to a percentage based on, what is typically being disinfectant and what isn't. And so what happens is the top return branch there through the pump that has 140 water, let's say you have 143 water coming back through that, because it's an open system, you're now permitted to enter or add cold water to the system to mix it back down to 140. And then in the lower branch, the 170, which is going to be coming back lower than 170, you will be able to mix up that water temperature to 170 because it's an open system. So again, there may be better ways to do this, more exacting ways to do this, but I just wanted to address the issue to make sure that everyone understood that we are thinking about the other part of the domestic hot water system when we're doing this. So to summarize the dual hot water source method, it is more expensive than the single hot water source method. Why? Well, we have 2 hot water heaters, an additional supply line, and 3-way valves versus 2-way valves, even though there won't be that big of an expense difference for a 3-way valve versus a 2-way. This type of implementation is obviously better suited for new construction because it'll be a lot easier to put that additional supply line in and hot water heater in under new construction. The big advantage of this system over the other one is it keeps all of the branches not being flushed in service. And again, because it's automated, it minimizes resources required and shortens the overall disinfection time. So a brief comparison of the 2 approaches. On the left, we're showing the dual hot water source with 3-way control valves, and on the right, single hot water source with 2-way control valves. So the dual hot water source with 3-way control valves provides keeping the rest of the system working when you're flushing one of the branches. While on the single hot water source, you're keeping the whole system out of service while the flushing is going on. So the first approach is the 2 hot water source is more expensive than the other one. On both of these, adding control valves to the input of these branches or risers gives tremendous amount of flexibility to the system and how you control it. So that's something really to focus on because it's a huge advantage once you have those controls and valves in place. In the 2 hot water source, as we talked about, it's more difficult and expensive to implement a flush through the supply line where it's inherent in the single hot water source method. So some further discussions and considerations on these approaches, especially with the dual hot water source. There has to be some more consideration being done on managing the return flow back to the 2 hot water sources as we discussed. You have to talk about flushing through the supply line trade-offs, whether you do it or don't do it. And 3, what we're doing now is we're adding components to the system. So in theory, anytime you add components to any kind of a system, automatically the reliability goes down because there is some chance of a failure. So you have to look at the risk you're taking. Even though this technology has been used over the years thousands and thousands of times, and all those devices are very reliable, you still have to look at the risk and manage your risk and determine if or where you need to add redundancy or if and where you need to add feedback devices or things like that to confirm certain operations. The other thing is flushing the high temperature water down the drain. We all know by code you're not allowed to do that. So you have to look at drain tempering alternatives if you're going to flush down through the drain. And also the possibility of flushing through an inline filter to help capture the Legionella bacteria. As I said very early on in the presentation, one size does not fit all. You typically need more than one Legionella mitigation method to really have an optimal working source there. So briefly on chemical flush, I'm not going to talk a whole lot about that. It is one of the other primary methods of Legionella mitigation. Basically what I'm going to say here is that a lot of the methods that we talked about previously can also lend themselves to chemical flush as well. I kind of directed this presentation over thermal disinfection for two reasons. One is to only focus on one of these methods because of time limitations. And the other one, full transparency, is I'm a lot more familiar and comfortable with thermal disinfection than I am with chemical flush. But definitely opportunities to use the same type of techniques that we used with thermal disinfection. Cost versus safety. So one of the things, now that we're normal flow that I showed in these diagrams is at 140 degrees. If you're doing more than 120 degrees, point of use mixing valves are required at each of the fixtures. And typically, when you're having a point of use mixing valve of each of these fixtures, by design, they're not permitted to have water flowing through them more than 120 degrees. So that makes things very difficult when you're trying to flush through the fixtures 160 degree water. So that's one of the trade-offs you have to make. Are you actually going to flush through the fixtures that most people recommend, or are you going to not do that because of the expense of it? There are devices out on the market that are called smart faucets that allow you to thermally bypass that hot water through the mixing valve. So again, it's another trade-off you have to make. Do we put in the expense of thermal bypassing smart faucets, or do we not flush through the fixtures and just keep our point of use mixing valves that we've been using? The other thing with cost versus safety, we've all experienced this year, 50 governors in our country had to make cost versus safety decisions. They had to trade off the economic issues associated with shutting down the state against the maximizing the safety of the citizens of the state. And so there's, unfortunately, there's no magic formula for that. Very difficult decisions. But in the end of the day, you're basically trading off cost versus safety. I spent a lot of time in machine guarding in a previous life, and the same thing applied there. We did a lot of work for pharmaceutical companies, and they all had to evaluate in their automation equipment, where it could be very dangerous for the operators. How much of safety do you want to put in there to protect the operators versus hurting production and slowing down the process and costing them more money? And it's no different with us with effective Legionella mitigation. You always are making those cost versus safety trade-offs. Now, the one thing I would say is I don't feel it's the plumbing community's responsibility to make those decisions of cost versus safety. I think it is our obligation to present those differences to, let's say, the building owners and outline the risk for them and let them make that decision, because in the end, it's really their ultimate responsibility for their patients and their staff. So in summary, some of the things that we discussed, again, Legionella mitigation is one of the very hot topics in domestic hot water systems, frequently discussed, a lot of movement in a lot of different areas of that. The healthcare industry is looking for engineering to community to help with these solutions. We've introduced two potential control concepts to automate that process. And again, I'll state again probably for the third time, these aren't the end-all type of solutions. Hopefully with the whole plumbing community involved with this and getting behind it, we can definitely improve on what I've shown today and further minimize risk to patients and automate the process. You need to analyze the cost versus benefit and the risk versus reward to find out what the best overall solution is for a given system. The ultimate goal, at least for me anyway, is to create awareness with the plumbing engineering community and foster discussions on this topic and integrate them into written standards. So next steps, I think the plumbing community really needs to build on this. I'd be more than willing to, in the interim, act as a coordinator for this effort until we get an association or some type of standards committee behind it, ready and willing to incorporate this type of solution in their other standards. I think it's extremely important. So to strengthen numbers, so if we all get behind this and coordinate the efforts, I think we'll end up with better solutions and more standardized solutions and best practices to move forward. So that's it. Thank you. Okay, everyone. Thanks for hanging in there for the 40 minutes. So the next thing we want to do is do some Q&As. We did get a couple questions in already that we'll answer. And then after that, if there's any other questions, we'll entertain them for the next 15, 20 minutes. So the first question we have here, let's see if I can find it. Okay, so it says, I thought your presentation was informative and timely, and what do you see as the next steps? First off, thanks for the compliment. So what I'm hoping to accomplish as the next steps is, number one, is everyone that's been on, spent the time listening to this webinar, appreciate any feedback that you can get if you have time to look at this and think about it. Forward to me any questions you have, concerns, etc. And then once I get those questions, I'll formulate answers to all those and put a summary together and send it back out. And then I'm hoping either people that are on this webinar session here, or maybe know somebody that is associated with one of the major organizations or a standards committee or something like that, would also have an interest in this and maybe give us some kind of a sponsorship to kind of move this thing forward. And then hopefully this ends up in either some existing standards or some new ones, and just kind of formulate some best practices and guidelines for everybody to follow. And then let's see, the next question. Looking at your sketch for the 2 hot water system, I noticed that what appeared to be a slight deviation from the single hot water system, and that there was no provision for making sure everything was set up for thermal disinfection of a given branch before the 160 plus water flowed through it. That's a really good observation. That's an oversight on my part. But if you remember this, the sketch we showed where I added a normally closed valve and also a 3-way valve to make sure we could disinfect the primary supply line, you could actually insert that 2-way normally closed valve into that secondary supply line, the 170, to ensure that you don't flush any hot water until everything is set up to do the flush of a given branch. So let's see. Aaron, do you want to take, there's one here about the water temperature?
Yeah, certainly. So it looks like, all right, so first off, my name's Aaron Markward. I'm Tom's partner in crime, as he mentioned in the beginning here. So we have a question that says, isn't the highest allowable temperature in any domestic hot water system, going to the drain, 140 degrees? How do you get around this when draining upwards of 170 degree water? So that is something that Tom did kind of point out during the presentation slightly. There is going to be very high temperatures going to drains at this point. And it just does so happen we do manufacture a product that will help out with this. It's called our drain tempering valve. There are a number of different valves out there, different solutions where you can install these, and what they'll do is they will combine your cold water line into the drain and basically use an actuator, a paraffin wax actuator, to sense temperature, and when it sees that there is too high of temperature going to these drains, it will open up and allow cold water to flow in, mix it down to under 140 degrees, and make you compliant with codes. So that is one solution. Make sure you do have something in place to mitigate anything over 140 degrees going down your drain, because most local codes do state you have to stay under that 140. And if you have PVC piping anywhere, it's going to melt if you put anything too high of temperature down there for especially an extended period of time, to 20 to 30 minutes, something like that. So our solution is the DTV from Thermomegatech, but there are other solutions out there as well.
Okay, and I have another question here. How addressable are the BMS building management systems to accommodate signal inputs from additional devices? And what are the common limits for the number of devices these systems can supervise? So, as I mentioned earlier, building management systems have been around for 30 plus years, and they've come a long way. And actually, two things. One is they basically are all implemented with a number of spare I/O ports, just as a matter of routine. But in addition to that, with today's electronics technology, they're all very expandable. I mean, there's no problem. I mean, they probably are handling in the larger buildings, well over 1,000 I/O lines, and they can easily add hundreds more without any problems whatsoever. So there generally really is no limitation on the number of additional inputs you can put into these systems. Now, that being said, there may be some older systems out there that may have limitations and may not have the expandability. So that's a good question from that standpoint. If you're trying to go do a retrofit into a building that has a system, you do need to make sure how expandable the I/O is if there's not enough spare I/O already existing. Let's see, I don't know, is there any? Let's see. Nice job, Tom. How important do you think flushing water out of the tap is? It usually a short leg and relatively small portion of the overall system. Doing so really complicates what's needed for disinfection. Hey, Mark, I totally agree with you. It does really complicate things, adds a lot of cost, adds a lot of safety issues. Unfortunately, I am not the person to tell you what the differentiated risk is by not flushing through the fixtures versus flushing through. But it really is a great question. One I will look into further myself, because I have been thinking about it as well, because it really does simplify the whole system if you don't have to flush through the fixtures. It's just that everything I've seen says that we have to flush through the fixture. So again, I think I will look into that and feed that back to everybody as far as what I can learn from it. And again, everything is a risk versus cost decision process. So I will look into that. It's a great question. See if I have anything else. No, I don't have anything else right now. If anybody else has any questions, we're still on here for a couple more minutes. I think, Nicole, were you going to put some closing remarks in?
Hello. So, Tom, I see a question here that I could actually take.
All right.
There's a slide that says CSUSF. What does that refer to at the end of the branch line on the hot water supply? And that is going to be, I believe Tom mentioned it in the presentation too. It is a balancing valve. It's a thermostatic balancing valve in particular. That's kind of one of our brands once again. So that just has the capability of balancing at balancing at a lower temperature, typically, like 120 degrees, whatever your normal everyday temperature would be, and then also your high temperature for your Legionella flushes, your disinfection flushes at 170 or 160 degrees.
Okay, Aaron, is that all we have, do you think, for questions then at this point?
Let me just take one more look through, make sure. Yeah, I don't see anything new. Yep.
And everyone, you have our contact information, and I guess maybe Nicole will give you more input on that, but feel free to reach out to us. I'm going to take any additional questions. I'm going to summarize it all and feed it back out to anyone who has an interest in this. Okay?
And this presentation is going to be available on demand immediately after we're done here. So if you want to take a look at it again, you'll be able to just go at it your own pace and do it that way. I do see a number of questions that address that.
All right, thank you, Tom, and thank you, Aaron. This is Nicole Meyer from PHCP Pros. I just wanted to thank you all for joining us today for the latest installment of our webinar series. Thank you to Thermo Megatech for sponsoring today's webinar, and many thanks again to Tom and Aaron for the fantastic presentation and Q&A session. All attendees will receive an email from us with more information on how to access a recording of this webinar, as well as an optional survey where you can let us know your thoughts. Additionally, if we did not get to your question during our Q&A session, we will try our best to email you individually with a response. If you are interested in attending more of these PHCP Pros webinars, you can find details on what we have currently scheduled on our website, www.phcppros.com. On our website, you can also subscribe to our e-newsletters so you never miss hearing about a webinar you may want to attend. Thanks again for joining us today, and have a great day.